All right, good morning, calculus students. It is Monday, March 30th, and this is your video for the week, introduction and some examples of the topics we're working on this week. It's a pretty important topic, and so I really want you to take the time in in Khan Academy to watch the video explanations. There are, I believe, a set of exercises also that I'm asking you to complete for your homework we do next Monday evening. I've extended the schedule a bit, as you'll see in what I posted last night in regards to what will be happening this week, since next week, of course, is only 3 days, and one of those is your workday. I'm extending the due date for the assessment, which I'll be posting at the end of this week, to Wednesday night at 11:59 p.m. Your homework exercises from Khan will be due Monday night at 11:59 p.m. And then I've assigned, as you'll see in your assignments that have due dates in Google Classroom, some problems for you to work on before we meet in our Zoom class on Thursday at the regular time at 8 o'clock on Thursday morning, which will be our last scheduled Zoom meeting before spring break begins. And so what I'm going to do today, and hopefully I can keep it under about 20 minutes, but I do want to work out two problems actually completely for you from the problem set that I've asked you to look at, which is on page 268 of your book, problems 23 to 33 odd. And I'm giving you the odd problems, so of course you can check your results in the back of the book in terms of the result or the answer, and then come with your questions on Thursday. In the meantime, of course, send me email questions about particular problems, or if you want me to make a video again of another problem worked out to post, I can do that. Just send me a note and let me know that's what you'd like. I will have office hours on Wednesday during the usual posted times, and then let me know if you have other times that would work better for you. So today, what I want you to do with your book is turn to page 262. This is where we'll start, and then have some paper out to take some notes as you go. I'll probably post the notes in Google Classroom tomorrow sometime. Okay, so we're working on this idea of finding the area under a curve, and you already know kind of the setup is to use the rectangle shape in order to approximate the area under a curve. We're considering a plane region, meaning a two-dimensional region. I don't know that we'll get to it, but of course you will eventually in a calculus course in college get to the idea of three-dimensional figures and finding volumes in that case rather than areas. Excuse me. But this is the basic setup, so please read through these examples carefully. I don't want to do that with you here because I want to get to actually working through a problem. So I will presume that you will have had a chance to read this entire section carefully, focusing on pages 262 through 266 for this week, and then looking at the two problems I'll be working out today. So that's your start for getting ready for class on Thursday at 8 a.m. Okay, so here's the basic idea, right? We have a function, in this case it's defined as a parabolic function, and there's two essential ways to begin with trying to make sense of what we're doing. The first is to inscribe the rectangles inside the curve. So you'll see that each rectangle is completely inside the curve. The right-hand side of this rectangle is actually touching the curve, okay? This would be underestimating, right? Underestimating the area, because these little sections of area under the curve that are not accounted for by the area of the rectangles. What we would do is find the area of each rectangle. They all have the same width, you notice, and then so we would take the width of the rectangle times the height of the rectangle. In this case, the height of the rectangle is determined by the right-hand endpoint of the rectangle, because that's the one that actually touches the graph. And where it touches the graph, of course, that's the function value of the graph, or the function value, the y value of this function. Okay, so the right-hand corner of this first rectangle in example 3 would be touching the curve right at that point. So the height of this rectangle is actually going to be the function value at 2/5, because that's where we touch the curve, and that's where the function value is. It's the value of f. It's the y value when x is 2/5. Okay, the height of this rectangle is going to be the function value at this right-hand corner. So it's going to be the function value when x is 4/5. Will be the height of this rectangle. So really what we're doing is we're using the function to determine the heights of the 4 rectangles, which makes sense because the height here is the y value, which of course is the function value. And then the width of the rectangle is actually uniform. So the width of the rectangle is determined by, well, it's determined by the entire the entire distance we are interested in here from 0 to this number, which is 10 over 5, which is 2, of course. So it's that entire distance divided by how many rectangles we're using. So we're using 5 rectangles to cover a distance of 2, right? That would be 10 over 5, which is 2, is the actual location here. But the width of each rectangle is going to be that entire distance, which is 2, divided by the number of rectangles. So that's 2 over 5 is the width of each rectangle. Okay, if we look down below, it's a very similar picture, right? Same function, same number of rectangles, same width of each rectangle. But now we're using the left-hand corner of the rectangle as is determined by the function. Okay, so you see the difference here is I'm inscribing the rectangles. Here I'm actually over the graph and I'm going to overestimate. Okay, so we call this the lower sum and we call this the upper sum. Okay, the lower sum is an underestimation of the area because we're inscribing the rectangles underneath the curve completely. This is an overestimation. This is the upper sum, okay, because we're now determining the height of the rectangle by using the left point of the rectangle is actually on the graph itself. Okay, but the sum is going to look very similar in the way we set it up. Okay, notice the sum, the area is going to be basically the height and the width of each rectangle multiplied, and then we're going to add up all the rectangles. So we're going to take the height of the rectangle, which is determined by the function value, either for this example at the right-hand endpoint, or for this example at the left-hand endpoint. So that's the height of the rectangle times the width. Well, every rectangle has the same width in both examples. So what you see the difference in these two is here the function value is of the right-hand endpoint, determined by which rectangle I'm talking about, which is determined by the index of the sum. Okay, so either it's the right-hand endpoint or it's the left-hand endpoint. But I take the function value times the width of the rectangle. I add that all up for all of the rectangles. And so what you're going to see is for an example like this, where I'm inscribing, the lower sum is 6.48. When I do it this way, the upper sum is 8.08. And of course, the answer, the actual answer, is somewhere in between. So the place we're headed with this is, all right, these are the lower and upper sums. What happens as I increase the number of rectangles? So as I increase the number of rectangles, of course, right, the width of each rectangle gets smaller, okay? And the difference between this sum, where I'm underestimating, and this sum, where I'm overestimating, gets smaller and smaller and smaller, and eventually we'll be able to say the actual limit as n goes to infinity, n is the number of rectangles I'm using. As n goes to infinity, these two things will converge on the same value. And the value that they'll converge on, of course, is the area of the function underneath the function itself. So this is the sort of this is a great example to look at to help you sort of understand what's going on with lower sums and upper sums. Okay, and then the rest of it is mechanics. It's just algebra, basically. Okay, so once you get this concept in mind, then the remainder of this chapter, this section in the chapter, is just sort of more explanation of how that actually works. And then if you look on page 264, okay, finding the upper sums and lower sums for a region, I'm going to work out an example. So the example I'm going to work out is going to look very similar in structure to this one that's in the book. So between this example, read through it carefully, and then watch what I'm doing for this problem out of the text. Excuse me. And then you should be able to try a couple of these on your own. It is messy. It is a little time consuming, but it's a really important exercise in algebra that you should be able to do this very carefully and precisely. Okay, so you will want a calculator handy because we are doing estimations using decimals. Okay, so the problem I'm going to actually work out, two problems actually, is number 28 and number 32. Okay, so number 28 is this problem. So I'm just going to zoom in on it one time, and then I'll be writing out my work actually on paper. So you're going to want to have this in front of you, but just a quick overview of what's going on. Here's my function, square root of x plus 2. Okay, so it's a square root function. This is the basic shape of a square root function. And we also know because of the +2, normally this would have a beginning at the origin, but it's been vertically translated up 2. So now it's actually starting at 0, 2. Okay, and we're interested in approximating, using lower and upper sums to approximate the area underneath this function between 0 and 2. So the region is shaded, and if you look closely, what you're going to see is you've got the sort of pinkish colored rectangles are the ones that are underneath the curve, inscribed. So the left-hand corner of each rectangle, top of each rectangle is actually on the graph. And then you also have these lighter blue rectangles are the ones where the right corner of the rectangle is touching the function, okay? So in each case, there are 8 rectangles, and the width of each rectangle would be determined by the entire distance, which is 2, divided by the number of rectangles, which is 8. So each rectangle has a width down here at the bottom of 1/4. Okay, and the height of the rectangle is going to be determined by the function value depending on whether it's a right hand or a left hand endpoint. Okay, so enough of the picture. We're going to go straight to the working out of the problem. So follow along carefully with the steps, and then go back and compare this to example 4 in your book, and you'll see the flow of how this works. Okay, so the first thing to notice is, right, n is 8. We have 8 rectangles. Okay, the delta x, which is just the width of our rectangle, is, right, the difference in the beginning and the end points of the x. So if we're going from 0 to 2, we're starting, the distance would be 2 minus 0 divided by n. So that's 2 over n. So in our example, delta x is 2 over 8. This is 1/4. Okay. I should write down here 2f of x is square root of x plus 2. Okay, we're going to need that. Okay, so in the terminology, you're going to see in example 4 in the book, the left endpoint is denoted by lowercase m with an index of I, right? I is your index. That's telling you which rectangle am I looking at. I is 1 is the first rectangle. I is 2 is the second rectangle. And we have 8 rectangles. So I is going to go from 1 up to 8. Okay, so the left end point is going to be 0, which is our starting value of x, plus I minus 1 times 2 over n. Okay, this is general, but n is 8 here, right? So really, what is it? It's I minus 1 times 2 over n. Why I minus 1? Because it's the left-hand endpoint, okay? So if I'm in the first rectangle, the starting point is going to be 1 minus 1 times 2, that's 0. So the starting point, the left end point, is going to be right at 0. Okay, the right end point, this is the left end point of the rectangle. This is the right end point of the rectangle. Okay, so I'm in the first rectangle. This determines the left end point of that rectangle, which is 0. So these are x values, right? These are x values. Okay, the right end point is capital M, also indexed by I. Okay, that's also going to begin with 0, and then it's going to add, but what's it going to add? Okay, it's going to add I times 2 over n. So we're going all the way to the right-hand side of that rectangle. So that's I, or 2I over n. Okay, so if I'm at the first rectangle, the left end point is 0, the right end point is 2 times 1 over n, which is 8, so that's 1 over 4. So I start at 0 and I go to 1 over 4. So these two give me the general form of the locations of my left hand and right hand endpoint of my rectangle on the x-axis. Okay, so now here's where the fun starts, and this is all algebra, right? So the lower sum, this is a lowercase s. It's not obvious. Let me make that a little smaller. Okay, the lowercase s is equal to the sum. So we're adding up the area of all the rectangles, and we have 8 rectangles from 1 to 8. Okay, and for each rectangle, the lower sum is going to take the left end point value of the graph. So that's the y value, that's the height. This is the height of the rectangle times the width of the rectangle. So this is height times width, There are 8 rectangles. I'm going to add all those up. Okay, so that's the sum from 1 to 8. The height of the rectangle, f of m, little lowercase m, so that's this thing. Okay, I have to put that into the function. Okay, so we're going to use lots of grouping symbols here because we don't want to lose any information. Okay, n is 8, so I'm going to put 8 in here, plus 2. So all of this is the function value at the left endpoint, times the width of the rectangle, which for every rectangle is the same. It's just 2 divided by 8, right? If I go back up here, it's this. So that's the width of each rectangle. So I have the height of the rectangle determined by the left endpoint times the width of the rectangle, and I have 8 of those, and I'm going to add them all up. So now I'm just going to simplify this sum by using some algebra. Okay, so the first thing I want to do, or by the way, so we're calling this is the lower sum. Lower sum, okay, because I'm inside, right? If I'm underneath the curve, the entire rectangle is underneath the curve. If you go back to the picture, you'll see these are the pink rectangles. Okay, so we're going to simplify this. Well, right, 1 over 4, it's a multiplier, and remember from our properties of sums, I can bring that outside. So that's 1 over 4 times the sum from I equals 1 to 8 of what? Okay, well, inside I have this 2 over 8 inside my square root. So I'm going to simplify that. I have I minus 1 over 4. That's just canceling the 2 into the 8 plus 2. Okay, well, I was going to string along my simplifying here. Of course, I have a square root and I have a 4 inside. So remember how to take square root of fractions. You take the square root of the numerator and divide it by the square root of the denominator. So that's I minus 1 over square root of 4, which is just 2. I still have this plus 2. Okay, keep going. All right, we got some, what are we trying to do? We're trying to get a number here. And there, right, there's the only thing we have inside here is the index. So eventually we're going to be counting this up if we can't simplify it any further. Okay, now we're going to do some more simplifying with sums, right? Remember, if I have a sum and I'm adding 2 things, I can break that up into 2 sums. So I'm going to take the sum of this part. Okay, and inside there, I'm going to do 2 steps at once here. I have a fraction of a half. I can just bring that out front, but not all the way out. It's got to be next to the sum because it's just right here. Okay, I'm going to take that out. And then I have the square root of I minus 1 plus the sum of just the number 2. Okay, so I just broke this thing inside because I'm adding. I can do the sum of this plus the sum of this. This 1/4 is all the way on the outside. It's multiplying times the whole thing I get here. Okay, believe it or not, we're almost done. So what does this actually work out to be? Well, what is the sum of 2 8 times? That's just 16. So over here at the end, I've got plus 16. Okay, that's all of this is just this, plus 16. Okay, and right here, I got the 1/2. And then let's look at what that sum, this part right here, actually is. It's just the sum from I equals 1 to 8 of I minus 1. So if I put a 1 in there, I get 0. So the first term is 0 plus. The second term would be 2 minus 1. The square root of 1, that's square root of 1. And then I'm going to go all the way up to, okay, when n is 8, this is 8 minus 1 is 7. Okay, well this, right, there's no way to simplify this. I'm just going to have to approximate this. But before I do that, let's do some more simplifying, right? I can distribute this 1/4 here and there. So that's 1/4 times a half, that's 1/8, times this sum. Well, I can simplify that a little, the 0 doesn't matter. And I'm going to get this. Okay, that's this. And then I'm going to take 1/4 times 16 is 4. Okay, now we get out the calculator. We're going to approximate this because this is an approximation anyway. So this is approximately 5.68. So that's the lower sum, is 5.68. And believe it or not, right, all this messy looking algebra, and all of this is algebra, is just adding up the area of rectangles, right? And the area of the rectangle comes all the way back to this. The height of the rectangle times the width of the rectangle. We add that up for all 8. Okay, if we do the upper sum, so again, please refer back to example 4. So this is a capital S, this is the upper sum. If you look at the formula or the sum notation, it's going to be all the same, or we have 8 rectangles, right? But now we're going to use the right-hand endpoint of the rectangle to find the function value times delta x. So this is capital MI, this was lowercase mi. So in our expansion, instead of using this, which we did the first time, we're going to use this. It's going to be a little easier. Okay, and I'm not going to write down as many steps this time. So it's going to be this, square root 2i over n is 8, plus 2 times still 2 over 8, or 1 over 4. Okay, so let me go quickly through how this works. Okay, so this is a little easier than the other one. Not a lot, but a little bit. Okay, we're going to break up the sums again, just like before. Okay, here's 16 again. And now it's just going to be 1 over 8 times, so that's distributing here, times the sum of the square roots from 1 to 8. So it's 1 plus square root of 2 plus square root of 8 plus 16, which is approximately 6.04. Okay, so we have a lower sum estimate of 5.68, an upper sum estimate of 6.04. The actual area is somewhere between these two numbers, okay, between 5.68 and 6.04. Okay, and very soon we'll be able to do this in a much shorter way. But it's very important that you understand the principle behind this is essentially adding up areas of rectangles. Okay, so that's problem number 28 worked out in detail. Okay, problem 32 is sort of totally different, but it's important because this is leading us to figure out the limit, right, of a sum. Okay, so this is going to stand for the sum just like here, right? It's the same thing, and it doesn't matter here whether this is a lower or upper sum. We're just given the end result of using our formulas to simplify sums. And this part in the brackets should look familiar, right? If you go back to your sums, this is just the sum of I squared from I equals 1 to n. Okay, but what we're looking at here is what happens to this as n goes to infinity. So think about n as my number of rectangles. This is this situation where somehow this represents the area of a single rectangle. What happens as n goes to infinity? What happens to this value of this thing? And this is, surprise, surprise, algebra again. Okay, so first thing to do in these problems is just expand everything out. It will notice the 6 can just come out here because it's just a constant. So we're going to get 64 over 6 times n cubed. Okay. Inside, we're just going to multiply this out. So n times n plus 1, that's n squared plus n, times 2n plus 1. Okay, and just a few more steps. 64 over n. Oh, sorry, let's reduce that. So 64 over 6 reduces down 32 over 3. Okay, and inside we're going to just expand this out and you can verify. You get 2n to the third plus 3n squared plus n. And then we just multiply that out. We're going to get 64. We're going to get 64 over 3 plus, distribute here, we're going to get 32 over n plus 32 over 3n squared. Cool. So this is just this. And the question is, what happens to the limit? Okay, what happens as n goes to infinity, n representing our number of rectangles in our situation, as this, so that's the limit, as n goes to infinity of 64 over 3 plus 32 over n plus 32 over n squared. Okay, so we got to think back to limits, right? What happens to this value as n changes? Nothing happens. It's a constant. Okay, what happens to this as n gets really big? Well, 32 over a number that's getting really big and bigger is 0. And the same thing here. As n gets big, n squared is getting big, and these numbers, this number on the top isn't changing, so this is 0. Okay, so the limit of this sum as n goes to infinity is 64 over 3. Okay, and you will see examples of that in the text as well. Okay, this was a long video, guys. It's really, really important that you go back and watch this in detail if you need to, and compare this to problem example number 4 in your text. Okay, and the main thing I want you to really get is the concept here. The concept is we are taking rectangles and using those to approximate the area under a curve. And this is building up to something called the fundamental theorem of calculus. Please read ahead if you'd like to know about that, but we'll come back to that after spring break. Okay, that's enough. Watch that video again, please, at least one more time. And then I'm going to call this quits. Take care, everyone. And I want you to just enjoy or get ready to enjoy your spring break by working hard this week and finishing up strong. Okay? All right, guys, take care. Talk to you soon.